All right, let's start. Good morning. How was the midterm? No? Yeah. Yeah, yeah. Yeah, we'll see. We'll see how it goes. I haven't started grading. There's a couple of students who, some of your colleagues that are going to take makeup and stuff. So after that, we'll see. Yeah. Yeah, so I guess the point here is that like when it comes to eigenstuff and beyond, even though in principle you could calculate everything, often unless you really understand the abstract math underneath a little bit, you can just keep calculating, and then once you make a mistake, it becomes impossible to figure out. You end up needing to taco and stuff like that. So yeah, we'll see. So this is our last week where we're going to discuss new material. And the next week, we have 2 classes, I believe, and I'm going to reserve those for review. And so you can bring some questions or problems for us to discuss in class for next week. If not, I think I'll just go through some of the problems or some of the exam questions from previous exams, discuss it in class in more detail and so on, even though you know, the keys are up online for the final. So initially, if you look at the syllabus, this week was reserved for dynamics, you know, applications, Markov processes, PageRank, whatever. But you know, it's not beneath me to let go of dynamics at this stage, because I'd rather you understand singular values and singular value decomposition. And then there's a couple of sort of related ideas. For instance, the pseudo-inverse, or you know, what is called Eckhart-Young approximation. So for instance, just using singular values, you can, you know, go ahead and take whatever matrix you want, and you can just find some sort of an inverse for it, even though it's not square in general, for instance. So that these kind of ideas, this is the Moore-Penrose pseudo-inverse that uses singular value decomposition. And as far as I know, for instance, Moore, I think, came up with this inverse or pseudo-inverse back in the 30s, and then in 50s or 60s, Penrose figured it out again, wrote another paper. And of course, like 50 years later, he got a Nobel Prize in, I think, physics. So Penrose is pretty cool. And then, yeah, okay, we'll discuss the other things as well. These are all downstream singular value decomposition. Okay. Now, instead of going into the abstract stuff, which I'm going to spend some time on also, the interpretation, just like we did for spectral theorem, I want to first start with some examples for the singular values. Okay. Now, you should imagine this, okay? You're talking to someone who hasn't taken linear algebra, but somehow this person that you're talking to knows eigenvalues are nice, they're important, whatever. And then this guy, for whatever reason, gives you some matrix that is not even rectangular and tells you, give me the eigenvalues. And then you try to reason with this person. You know, that doesn't even make sense, you see? It's like, it has to be symmetric, or it has to be a square matrix to begin with for me to be able to even talk about eigenvalues. And of course, the person could not understand what is really being said there. It's like, if I don't understand this. It's like, I need a matrix, I need some numbers. Important numbers are supposed to be eigenvalues. I want you to give me eigenvalues. I thought you had taken linear algebra. I thought you could do these kind of things. So this is the context, okay? And so what we're going to try to do is we're going to take some arbitrary matrix and try to fit it into the spectral theorem. Because at this point, even though, you know, in principle, you could try to compute eigenvalues of a square matrix, we know, you've learned from the exam, for instance, that it's not as straightforward. But if you could come out somehow start with whatever matrix you have, resemble it to a symmetric matrix, then you can just use the spectral theorem and start doing things. So let's start with this. Say your matrix is a vector. That's a 3 by 1. It's a matrix. I want eigenvalues for this. Okay? I can't quite do that, but you see the replacement for the notion of eigenvalue is going to be singular value. Okay? So want eigenvalues of x. The proper word for it is the singular values. Correct terminology. Singular values. I'm going to define it later. Okay. I kind of mentioned this. I want to sort of resemble this X matrix to some sort of a symmetric and square matrix, consequently. Well, I have two options. I can look at X transpose X or XX transpose. One of them is a 1 by 1. The other one is a 3 by 3. Okay. So let's first look at the simpler one. Is this. Okay, this is this. So it gives you 6. Okay. Of course, we know that this is nothing but the norm squared, right? Because this is x inner producted against itself. Okay. So 6, in a sense, is an important number that we can associate to this matrix. But really, when you think about X transpose X, well, this is approximately something like x squared. It's just that I cannot just take the square of x this way. Matrix algebra breaks down. This is sort of one of the best things, one of the next best things you can do. But in any event, this number, instead of rather this number, I should be looking at the square root of it, which of course corresponds to the norm. Okay. So sigma 1 is going to be x norm, which is root 6. And I'm going to call this, I could have called this just the norm of x, but if I'm just interpreting this as an arbitrary matrix, I want to call it the first singular value. Top or first singular value of x. Okay. Once we define singular values, more generally, you're going to see this sort of fits right in. It kind of makes sense, I hope you would agree with me, because singular values are supposed to be something like eigenvalues, meaning they should be sort of important numbers associated to matrices. Well, if my matrix is a column matrix to begin with, certainly its magnitude, its norm, is an important number. So the magnitude norm should be a singular value. Okay? I'm just developing some sort of an intuition. But of course, here's the next step. Instead of looking at this symmetric matrix, I could have done it the other way around too. I could have taken the outer product of x with itself. In which case, I'm going to get a 3 by 3. Okay, this is the outer product. Okay, this is going to give me 3 by 3. What is this? This is 4, 2, 2, 2, 1, 1, 2, 1, 1. Okay, what can I say about this matrix? For instance, what is its rank? 1, exactly. So when you're outer producting two vectors like this, the rank is always going to be 1, or at most 1. If you start with one of the vectors 0, then the rank is going to be 0. Why? Well, imagine starting with this. Well, in a sense, this left matrix already tells you the row operations you should be doing. Right? So it says, oh, the second row, or maybe the first row is twice the second row, and likewise the second and third rows are the same. This has rank 1, for instance. Okay? Consequently, nullity is 2, remember from the fundamental theorem, meaning this is not invertible, meaning its determinant is 0, okay, meaning one of the eigenvalues has to be 0. Okay. Let's try to compute. Oh, what else can we say about this matrix? This is a very nice matrix, even beyond the fact that rank is 1. It is a symmetric matrix. Okay, so that's good. Spectral theorem guarantees that all eigenvalues are real. I know that this has an orthonormal basis. All of these need to be computed, of course, but at the very least, I know what I'm expecting. Okay, so let's write it. Let's write these observations. Rank 1. X transpose is symmetric. Hence, spectral theorem applies to it. Well, let's write these as well. And what did we say? Rank is 1. The space is 3-dimensional. Fundamental theorem of linear algebra says rank plus nullity equals the dimension of the space, which is 3, which means that the nullity is 2. Nullity of X transpose is 2. Well, could I interpret the nullity of this matrix in terms of eigenvalues? What can I say? Nullity, let's write it slowly. Nullity of this matrix, by definition, is the dimension of the null space of it. Nullity of XX transpose. Which is the dimension of the null space by definition. Well, the null space of XX transpose is the same thing as 0 times identity minus this. Because the nullity of a transformation is the same thing as the nullity of minus the same transformation. But if this is the case, 2 is also the geometric multiplicity of the eigenvalue 0. Okay. So, what does this tell me? I have 3 possibly repeating eigenvalues for this guy. They are all real by the spectral theorem, and I know 2 of them has to be 0. So there's a third eigenvalue that is missing. Okay. Well, it should be this guy, of course, but we're going to see how that shows up. Let's just calculate this. Singular value decomposition is going to tell you that the missing eigenvalue has to be this. So you see, even though certainly this matrix and this matrix are very different, somehow they're intimately tied to each other at the spectral level. Okay, so let's compute the characteristic polynomial and so on. At this point, I know that the characteristic polynomial of XX transpose is going to have a factor of lambda squared. Because why? Because I know that AM of 0 is lower bounded by this, which means in the char poly, I should be seeing lambda minus 0, that is to say lambda, at least 2 times. Okay, and in this case, since there's a third eigenvalue, it has to be exactly 2 times. So I'll write this as well. And I know that the third eigenvalue cannot be 0 because if it were, nullity would be 3. Okay? Because the rank is 1, there's, I know, at least one eigenvalue that is not 0. Since this, what did I say? Oh, lambda squared has to divide char. Okay, let's try to compute this characteristic polynomial using standard methods. You see, spectral theorem allows you to interpret things and perhaps deduce certain things with minimal calculation. But ultimately, if you really want the specific value, well, you're going to have to go ahead and calculate using the determinants, whatever. So I'm looking at this. So lambda I minus this matrix. Let me just fast forward this part a little bit. Oh, that's a 4. That's a minus 1, minus 1, minus 2, minus 2, minus 2, minus 2, minus 1, minus 1. Okay, we need to compute this determinant. Let's go ahead and compute it. I'll use the triangle method. This, minus 4, this, minus 4 again. These are the positive sides, and then with the negatives, I have this other thing. This part, so that's 4, that is 4 lambda minus 1. And then this, plus 4 lambda minus 1. And then this, plus lambda minus 4. Okay, let's go ahead and compute how to do this. We're just going to have to expand everything. There's no straightforward way of doing this. Yeah. Lambda squared minus 2 lambda plus 1 minus 8. And then here I have a minus 4 lambda minus 4 plus 4 lambda minus 4 plus lambda minus 4. Okay, I'll leave this here. Expand the first guy. Lambda cubed minus 2 lambda squared plus lambda minus 4 lambda squared plus 8 lambda minus 4 minus 8. And then there I have what? 4, 8, 9 lambda. That's with a minus. And then 4, 8, 12, that's with a minus, but with an additional minus, that gives you a plus. Factorize into powers of lambda, like this. 1, minus 2, 1, minus 4, plus 8, minus 12, minus 9. Okay, that's good. That vanishes. Plus 12, that vanishes. And that's it. This gives me lambda cubed minus 6 lambda squared. Oh, this is beautiful. That's 0, that's 0. Okay? So you see, 2 eigenvalues. You see, one of them is 0, repeating. The other one is 6, which is exactly this. Okay, so maybe I should write it for both of them. So this guy, so you see, this is a 1-by-1 matrix, but it's a 1-by-1 matrix. It's a symmetric matrix, whatever. So everything works still. It's a 6. I'll draw the blip as well. Somewhere here. That's 6. Okay, this is this side. On this side, I have spec equals 0 and 6. And so what is the blip? Spectrum picture. You have one blip at the origin, and then you have one at 6. Okay. Any comments or questions about this so far? Okay. And again, I want to say that the first singular value of the matrix X is the square root of this guy. And here too, you see, I have 1, 0, and then 1, 6. The non-zero eigenvalues are going to match, okay? But, you know, this matrix, XX transpose, is of a different dimension than X transpose X. So there has to be some discrepancy. Well, what's going to happen is that non-zero eigenvalues of XX transpose and X transpose X are going to match. However, in general, you should expect one of them to have some padding like this. Some of them, so in this case, this is of larger dimension. It has a bunch of zeros that is not duplicated over there. Okay? Okay. Any comments or questions about this? Okay. Let's do something slightly more complicated. Well, what if I start with a matrix to which spectral theorem already applies? Okay. Say I have a diagonal matrix, in fact. What if I were to do the same thing? What happens? So say I have a 2 by 2 that is diagonal, say. I have a matrix A. I look at A transpose and A transpose A. Well, in this case, they're going to be the same. So maybe we should be looking at a non-symmetric matrix. Yeah, let's look at that one. Consider A, 0, 2, 1, 0. Okay. That's a matrix. Again, I want to get the eigenvalues for this, but this is not symmetric. Oh, I guess I can get the eigenvalues in this case. So let's go ahead and compute the eigenvalues. Okay, so char poly is determinant of lambda lambda here, minus 2 minus 1 here. AD minus BC gives me lambda squared minus 2, which is lambda minus root 2, lambda plus root 2. Okay, so it has two distinct eigenvalues. One of them positive, the other one is negative. And if I were to draw the blips, these are going to be outside the unit circle, like so. Okay? I could come up with the eigenvalues. But in a sense, you could say, okay, so this is nice, but you know, it's kind of harder to imagine what this minus root 2 does. Of course, along a certain direction, that means that my matrix acts as multiplication by minus root 2. But in principle, you want to rephrase everything in terms of stretch factors. And so let's try to go ahead and do the same stuff. That is to say, look at A transpose and A transpose A, these two matrices, and see what kind of a number we obtain that way. So now I'm looking at this product. Oh, 0. Okay, what is this? This is 1, 0, 0, 4. Very nice. That's a diagonal matrix. Everything is really good. Okay. I believe I made it correct. Let me see. Yes. So spec is this, 1 and 4. And the picture for the spectrum is like so. One of the blips is on the unit circle. The other one is here. Okay. In a sense, I would suggest that this is a much better picture than this, because you see now you don't need to worry about negative things. And in fact, what you can do is you can take the square roots of these and call sigma 1 of A to be 2, square root of this, the top singular value. And then the second singular value is going to be 1. That's a 2. Okay. So somehow I would suggest to you these two numbers are a lot more expressive even for this transformation compared to these. Why? Because the determinant of this is this by this minus this by this is minus 2. So if you forget about that minus, this stretches things by a factor of 2. And so the fact that sigma 1 is 2 is more compatible with this volume stretching that we were talking about all the way back when we first started talking about determinants. Okay? If I were to look at the other matrix, that is to say AA transpose, now I'm going to get something else, it seems. Let's do it. This time I'm looking at this matrix times this matrix. Oh, yeah, it's pretty much the same matrix. 4, 0, 0, 1. See, this is not quite the same thing as this, but certainly it has the same spectrum and the same numbers pop up. Well, I'll just write it. Okay. Okay. Any comments or questions about these two? So what is the main idea then? If I start with an arbitrary matrix, I can look at A transpose A and AA transpose, they're automatically going to be symmetric. And another thing too is that the eigenvalues of these AA transpose or A transpose A is always going to be in this ray. Okay. So when you're looking at the spectral picture of a matrix of the form AA transpose, you're going to be able to say that all eigenvalues are going to be in this ray, in this positive x-axis ray. It's going to avoid all other spaces, including negative eigenvalues. Okay. Any comments or questions? Okay, let's do a perhaps more complicated example. Again, I'm going to look at the 2 by 2. Maybe we should do a 2 by 3 perhaps. Let's do a 2 by 3. I'll add one more row here. Okay. Now I can't even quite look at eigenvalues of this right from the get-go. But the same trick is going to work. I can look at A transpose A or AA transpose. Both of these are going to be, in fact, symmetric and square matrices with eigenvalues always non-negative. Okay? So let's just look at this guy first. So this is 2, 0. Hang on, start the way around. So first column becomes first row, like this. And then I have 0, 1, 0, 2, 0, 1. So you see A transpose A is going to be a 2 by 2 for me. So that's a 1 over here, then it's a 0, then it's a 0, then it's a 5. Okay. In a second, I'm going to switch to a more complicated example. In any event, we have this nice matrix. Again, this is diagonal. Spectrum is 1, 5. I see 2 blips. One of them is on the unit circle. The other one is over here. Singular values of A are going to be the square roots of these numbers. Because looking at A transpose A is almost like applying A twice. Okay? So sigma 1 of A is going to be the square root of the top eigenvalue of this A transpose A matrix. And the other one is going to be 1. Okay, singular values of A. Okay. Now, if I were to look at AA transpose, at this point you should expect that one of the eigenvalues for AA transpose should be 1, the other one should be 5. There should not be any other positive eigenvalues, meaning the third eigenvalue should be 0. Okay? Yeah.
So why do you apply the square root to the first value and not the second one?
I am applying. What do you mean?
Oh, I'm dumb, sorry.
Yeah, no. Yes, exactly. No, that's good. Yeah. So let's look at the other matrix, A transpose. Now this is going to be a 3 by 3. Like this, and then like so. 3 by 3. That's a 4. 0, 2, 0, 1, 0, 2, 0, 1. Okay, that's a symmetric matrix again. Again, I hope my expectation is one eigenvalue is going to be 1, the other one is going to be 5. The third eigenvalue has to be 0 now. Okay, the third eigenvalue has to be a padding. That is caused ultimately because A transpose just happens to be of a larger dimension compared to this guy. Okay, let's go ahead and compute. Right, so lambda, 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 minus 4, minus 1, minus 1, and then 0, minus 2, minus 2, 0. Okay, we'll use the triangle method. Lambda minus 4, lambda minus 1 squared. And then this is 0, this is 0, that's fine. Minus the product of these, 4 lambda minus 1. This is 0, this is 0. So that's it.
Sorry, isn't it char A AT lambda?
You're good. Yeah, thank you. Apologies. I'm looking at, yeah, because I cannot just look at the characteristic polynomial of A itself. That is not defined. Thank you. So I need to simplify this. In this case, I can already factor out lambda minus 1 and write it like so. Lambda minus 4 times lambda minus 1 minus 4. Let's consolidate this a little bit. I'm running out of space over there. So I'll put a star here and transport or teleport over here perhaps, yeah. What was it? So yeah, I need to expand that. Lambda minus 1 times lambda squared minus 5 lambda plus 4 minus 4 is 0, so that's it. Okay, this factors out, and I get lambda, lambda minus 1, lambda minus 5. Spec of AA transpose, therefore, is 0, 1, 5, as I promised. Okay, look at the spectral picture. It's the same spectral picture that we obtained over there, except that you have an additional padding, which is this 0 blip over here, corresponding to this. Okay. Yes.
So do we call 0 a singular value or just the non-zero, like the ones that they share? We're not calling 0 a singular value. It's better, yes. I just made it up here, but it seems down the road in the theory it becomes easier to just not count this 0 as a singular value of A. Just associate positives. I think people use it either way, because it might also happen that both, so it might happen that some of the shared eigenvalues between these two are 0 to begin with. That can happen too. So yeah. Okay.
Any comments or questions about these? Okay, let's perhaps start doing a more complicated example. Again, numerical, and then tomorrow I'll transition to the theory as to why this works the way it does. Or maybe even before that, let's try to summarize the definition and the general properties that we can just deduce. Let's see. Okay, definition. Let A be m by n consider A transpose, which is m by m, and or A transpose A, which is n by n. Both of these matrices are automatically symmetric, and their eigenvalues are non-negative. Are automatically symmetric, and therefore spectral theorem applies to both of them. And not only are their eigenvalues real, but in fact their eigenvalues are non-negative. Okay. They share the same eigenvalues. Well, they share the same positive eigenvalues with the same AM and GM. Okay? Same positive eigenvalues. With the same algebraic multiplicity and geometric multiplicity. Since you have only finitely many positive eigenvalues, so in the picture they look like this. Okay? You can list them, and it is conventional to list them in a decreasing order or non-increasing order. When you look at the square roots of these eigenvalues, positive square roots, those positive square roots are defined as the singular values of A. Or maybe to be specific, non-zero singular values, or positive singular values of A. If mu1, mu2, mu r, okay, let's write it like this, are the shared positive eigenvalues their square roots, the positive ones, are defined as the singular values. And here I mean with multiplicity. So you see, mu2 could be equal to mu1 in principle. Then sigma 1 of A is mu1 in square root. Sigma 2 is square root of mu2 dot dot dot. Sigma r of A is mu r in square root, which is a positive number. These are the singular values of A. Are the positive, say, to be more specific, positive singular values of A. That's the definition. Okay. One final thing. What is R there? I used an index. R is the number of non-zero eigenvalues of A transpose A or AA transpose. What can it be?
Wouldn't R be whichever is the minimum between M and N?
Not quite. It could have, some of them could be zeros, some of the eigenvalues could be zeros. It's going to be upper bounded by the min of M and N. It's going to be rank, and it's going to turn out that the rank of this is the same thing as the rank of this, which is the same thing as the rank of this. That's magical. See, everything that we discussed so far in this course, they come together in this definition slash theorem, I guess. Okay. Now, tomorrow, we're going to see more examples, more numerical examples, and I'm going to start talking about the sort of different parts of this. Thank you. All right, let's start. Good morning. I'm going to take attendance. Start with you. So yesterday we started talking about singular values. There's more. Singular values were basic eigenvalues, but adapted to more general matrices. We just took whatever matrix and multiplied it by its transpose to get a symmetric matrix. And then we looked at eigenvalues of that symmetric matrix, and then took the square roots of those numbers, and those were the singular values. Well, much like the context of eigenvalues, we would want eigenvectors, or rather analogs of these. Well, the analog of an eigenvector is going to be what is called a left or right singular vector. It's slightly more complicated in this context, but it's fairly natural. And then once you compute these singular vectors, again, much like in the context of this spectral theorem, we would want to put these singular vectors in matrices to come up with a matrix factorization. And also, we would like to be able to write our original transformation as a linear combination of rank 1 matrices. OK. So let me remind you the 3 examples that we did last time. These were somewhat simpler. I want to do one more example that is perhaps more complicated. Example 1, well, I started with a 3 by 1. That is to say, I started with a vector, 2, 1, 1, 1, 2, 1, 1. And so in principle, we can again look at x transpose or x transpose x. And you can come up with singular values. In this case, we came up with only one singular value, which was the norm of x, which is root 6. OK, that's example 1. Second example was this 2 by 2. 0, 2, 1, 0. And then we computed 2 singular values. sigma 1 is 2, and sigma 2 is 1. It is conventional to index the singular values in a decreasing fashion. So sigma 1 should be the largest one, and so on. Example 3 was this matrix. Like so, and then 0, 1. And then we again came up with two singular values. Sigma 1 was root 5, sigma 2 was 1. Okay. Now let's try to remember what the whole procedure was. You start with whatever matrix you have. Okay? You look at, say, AA transpose. It is always the case that eigenvalues of this are non-negative. So this is always symmetric, and the proper terminology for, oh, the matrix has all eigenvalues non-negative is positive semidefinite. Okay? Positive semi-definite. This just means all eigenvalues are greater than or equal to 0. Okay? Some of them could be 0, but you're going to have some positive eigenvalues for AA transpose. The number of positive eigenvalues you're going to get for AA transpose is going to be exactly the rank of A. This with multiplicity. Number of positive eigenvalues of A transpose. This with multiplicity. So some of the eigenvalues that you obtain could be repeating. Then you look at the square roots of those, and those are going to be the singular values of A, or at least the positive singular values of A. Are the singular values of A. And again, it is traditional to denote singular values by sigma 1, sigma 2, whatever. Okay? Now I'm going to define a capital sigma matrix. That's, again, sort of notation that is common. Made up of essentially these singular values on the diagonal. But in general, the sigma is going to have the same dimensions as the original matrix, which means that you're going to have to pad with a bunch of zeros so that you have the same shape. Okay? So for instance here, capital sigma is going to be root 6, 0, 0. Okay? Here, capital sigma is going to be 2, 0, 0, 1. And here, capital sigma is going to be this. It has to have the same dimension as the original matrix. You put the singular values on the diagonal, so root 5, 0, 0, 1, and then you pad so that you have the same dimensions as the original matrix. You don't have to technically do this, but I think this is how it is stated in the textbook. It's easier to remember also. So. But really, when I see these things, I'm thinking of it as a block matrix, like so here, and here like so. It's better to think of it as a block matrix. Okay. Let's see. Okay, so ultimately, since, oh, of course, I can apply the same thing to A transpose A2 and everything works and blah, blah, blah. I'm going to do another numerical example in a second to just go over these ideas again. But let me mention this. Ultimately, as this guy is a symmetric matrix, I can apply the spectral theorem to it, which means that consequently, not only can I compute the eigenvalues of it, rather in a straightforward fashion compared to more general matrices, but also its eigenvectors have special properties like orthogonality, whatever. So the eigenvectors of this matrix and eigenvectors of the other way around matrix also are going to be called the singular vectors of A. So in this example, I'm going to try to compute those also. Are there any questions about anything so far? Okay. Let's see. There's this example in the textbook, but numbers are a little bit too large for my taste, so I'm hesitating. Well, let's go ahead and try to calculate it anyway. So now I'm going to look at a 2 by 3. It's this matrix, okay? It's an integer matrix. 4, 8, 11, 7, 14, minus 2. Okay, I want all singular values. So what should I do? How can I start even calculating things at this stage?
I mean, you can just start by doing AA transpose.
Yeah, so I can look at AA transpose or I can look at A transpose A. Which one is better? Which one is a better choice?
I like A transpose. Transpose directly.
So there are two options, okay? You can look at this or you can look at this guy. And somehow, even though in principle these are going to be distinct matrices, their eigenvalues are going to be tightly interconnected in the sense that positive eigenvalues of this is going to match with the positive eigenvalues of this with the same AM and GM. Okay, so these are like synchronized somehow. We're going to talk about why that is the case later. But if that is the case, okay, one of these is going to be a smaller matrix. It's often easier to go for the smaller matrix to compute things. Okay, right? So if I were to look at this, this is going to be a 2 by 2. This is going to be a 3 by 3. Okay, so this is better to compute. Okay, so for instance, in this matrix, I could have looked at, so I did look at X transpose, which gave me a 3 by 3. We computed the characteristic polynomial, whatever. But instead of doing that, if you were to look at X transpose X, that's just a number. You see, it's much simpler. So always look which one is the smaller matrix and try that one first. The other one is going to match anyway with the eigenvalues. Okay, so this is 2 by 2. This is 3 by 3. Let me record it here again. These two matrices are going to have the same positive eigenvalues with the same AM and GM. Are always going to have the same eigenvalues, same positive eigenvalues. With the same AM and GM. Okay. Because that is the case, and since I'm looking at singular values, I'd rather go for the smaller matrix. Okay. And even before continuing, what I can say is this. This is going to be a 2 by 2 matrix. It's going to have at most 2 eigenvalues. Well, exactly 2 possibly repeating eigenvalues. This is 3 by 3. It's going to have 3 eigenvalues. But since the positive eigenvalues of this and this has to match, this has to be, so 0 has to be an eigenvalue for this, even without computing, okay? So go for the smaller one. Now you need to compute. So you see, somehow, mysteriously, this matrix, even though it is a smaller matrix, contains the same information as this matrix. Well, part of it is that computing this is approximately of the same complexity. So let's just compute. That's A. Now I need to take the transpose of it, like so. Now this is going to give me A 2 by 2. So that's 16 plus 121 plus 14 times 14 is 196, I think. Oh. 96. Let's just check it on the side. So that's 6. It's a 5. OK, that's correct. Then I'm going to have this. Right, so what is that? That is 32 plus 77 minus 28. Now remember, this matrix is always going to show up as symmetric, so you actually don't need to compute this guy either. It's going to be the same thing as this. And in this, you need to compute. So 64 plus 49 plus 4. Did I make a mistake? Oh, yeah. OK. So consolidate. OK. If I add these two, that's 7, that's 1, that's 3. And to this, if I add 16, that's 3, 3, 3. OK, that's that. Now I need this number. This minus this is, or this plus this, I guess, is 4. The other one is 77, 81. That's 81 also. And what is this? OK, so I guess 68 plus 49, 7, 1, 1. OK. I mean, I don't know if you know these rules, but for instance, I can immediately say that I can take a scalar 9 out from this to simplify this any further, because all of the entries are multiples of 9 when you add the digits. 3 plus 3 plus 3 is 9. This is also 9, whatever. So these are all like multiples of 9. I can simplify this if I want, but maybe I should do that, in fact. So this is going to be 9 times something. That's 9, that's 9. 3, 3, 3 divided by 9 is, that's a 3, 27, 6, 3, 7. Very good. So that's prime. I can't go any further. If I try to divide this, I get again 27 here. That's 13. That's as far as I can go here. I can't simplify this matrix any further without using rational numbers. OK? So this is AA transpose. Now I need to compute the eigenvalues of this. I know right from the get-go, as this is a symmetric matrix, all eigenvalues are going to be real. And again, a special property of matrices, symmetric matrices of this form, is a positive definite property. Meaning, even before calculating, I know that I'm not going to get a negative eigenvalue. Okay? All eigenvalues are going to be 0 or +1, or positive. I'm thinking about if I can get rid of the scalar in a simplified manner. Yeah, I can just, I guess, look at, yeah, let's go ahead. Compute. What is the char poly of this? This is determinant of this matrix. So lambda minus 9 times 37, 9 times 9, 9 times 9, and then lambda minus 9 times 13. And what is this? This is this times this minus 9 to the 4. Okay. Expand. Lambda squared minus this and this gives me 50 times 9 times lambda. And then 9 squared times 13 times 13, 37 minus 9 squared times 9 squared. I'm trying to guess. There's some symmetry here. See if they computed it here. Okay. I'm just going to cheat. I don't want to keep computing this, but this is, you can apply the quadratic formula, whatever. It turns out that the spectrum of this is, I think, 90 and 360. Yes. Okay, two numbers. Therefore, the singular values of A are the square roots of these. I'll write it here. Sigma 1 is 360 in root, which if you want you can write as 6 root 10. And sigma 2 is root 90, which is 3 root 10. These are the singular values. Of A. And consequently, the capital sigma matrix is this and this in the diagonals, and then you need to pad. And again, capital sigma is going to be a matrix of the same dimension as A. And so you start with these numbers in the diagonal, and then pad it using 0 so that you have the same shape. Okay? What else can I say? Well, this matrix is 2 by 2. It has two distinct eigenvalues. As you see, these are positive eigenvalues. Algebraic multiplicities of both of these is going to be 1. That's by definition. And therefore, GMs are 1 as well. And if I were to look at this other matrix, even without computing, I know that one eigenvalue is going to be 90, the other eigenvalue is going to be 360, and the third eigenvalue has to be 0. Okay? So let's write that as well. Um, 0, 360, 90. Now, both of these are sort of important, even in applications. It's just that for purposes of calculating eigenvalues or singular values, it's often better to choose a smaller one, okay? Because presumably, ultimately, you're going to use a computer to compute, and then approximating or calculating exactly eigenvalues of a smaller degree polynomial is much easier, much safer compared to higher degree polynomials. So for instance, if I had gone ahead and tried to compute eigenvalues of this, the char poly of this was going to show up as a degree 3 polynomial, and lambda was going to be a factor for it, because that's what it means for 0 to be an eigenvalue for this. Okay, any questions so far? Okay, now ultimately then, what I would want to do is, somehow I would want to say up to a passive transformation, A is this matrix, just like in the spectral theorem, right? Like I want to have a factorization. I certainly have factorizations for this guy, and maybe using those, I can put them together and somehow get a factorization for A. And that's the idea of SVD, ultimately. I'll erase this middle part. You don't need this calculation anymore. Well, maybe I should record that this matrix is 9 times 37, 9, 9, 13. So let's write this. Both this and this are symmetric, and therefore, to both of them, spectral theorem applies. Therefore, I can find orthogonals for both this and this such that things happen, right? Is 2 by 2 symmetric? Maybe we can call D to be the diagonal matrix with the entries of the eigenvalues. Okay. Then by the spectral theorem, I have a 2 by 2 orthogonal. Let me think a second. Where do I want it? I'm going to call it U. Okay. Then by spectral theorem applied to this matrix, spectral theorem, there is a 2 by 2 orthogonal U such that this happens. I just apply the spectral theorem to A transpose. Okay. But of course, I can apply the same thing to A transpose A. A transpose A is 3 by 3 symmetric. And instead of this diagonal, you see now I'm going to have the diagonal, and I'm going to order it in the same way, but I'm going to have one more entry, which is going to be 0. Let's call that E. It's going to be this 3 by 3. And again, I want to think of it as a block diagonal, really. What is important is that this top left corner is the same diagonal matrix as before. by the spectral theorem, there is a 3 by 3 orthogonal V such that things happen again. Spec theorem. There's a 3 by 3 orthogonal, which we're going to call V. Such that A transpose A is factorized as V E V transpose. Okay. Any comments or questions?
What is spectral theorem again?
What is spectral theorem?
Yeah.
Spectral theorem says any symmetric matrix is orthogonally diagonalizable. Yes. It literally says that this factorization works and this factorization works for symmetric matrices. Should I remind you again? We had spent the whole week last week, but for the final, you need to know the spectral theorem. So you should not be asking for the final, what is spectral theorem? Spectral theorem is this nice feeling you get once you see a symmetric matrix, okay? It's this, oh, things are nice. Can do things, can compute. That's the spectral theorem. Okay. This is like one of the most important things, and no shame in not remembering, but for the final you need to remember this, and even beyond too. Like, at the very least, you need to understand, you need to remember spectral theorem is a good thing. Okay, if you have a spectral theorem in whatever context, things are nice. Okay, now let's see. What do I want to say? Here's a riddle, okay? Of course, I can go ahead and compute these guys at this point, this U and V, right? So U is supposed to be an orthogonal matrix, and therefore its columns are supposed to be orthonormal, which therefore means, since it is also supposed to satisfy this equation, each column of U should be an eigenvector for this guy. Okay? And similarly for this guy. V is supposed to be 3 by 3. Each column is a three-dimensional vector. They should constitute an orthonormal basis for R3. And all of these should be also eigenvectors for this other matrix. The riddle is this, okay? Say I'm not changing the diagonal, so I'm not sort of shifting, sort of permuting the orders. If I'm not allowing the eigenvalues to be reordered, is U unique? Is a unique orthogonal matrix that fits into this equation? This really goes to the heart of the whole issue that we're going to encounter in a second. So let's try to visualize what is happening. Let's just look at U because it is two-dimensional. It's easier to visualize. I'll leave that there. It's going to be like this. Okay, so 2 by 2. Columns are orthogonal, and they're orthonormalized. So this is an O and EB for R2, adapted to that matrix. So adapted to this symmetric. How does this look? Well, I don't quite know. I haven't computed things at this stage. But at the very least, I know that u1 is going to be perpendicular to u2. So I'm going to see a cross somehow in the picture. Say it's like this. Okay? So this is going to be, say, u1 is like so. And this is u2. So that consequently, since u1 is supposed to be associated to this line is the eigenspace associated to 360 for AA transpose, and the other line is the eigenspace associated to 90. Okay? So maybe let's write it as well. So you see both of these stretch, but this stretches much faster under AA transpose, of course. That's a 2 by 2 symmetric that I have. Okay. The question is this, what I'm asking. If I were to, so is this O and EB the unique choice that would work? The point is this, okay? In this picture, there's some symmetries. Namely, instead of u1, for instance, you could have chosen minus u1. If u1 is of unit length, so will be minus u1, and it's certainly going to be still orthogonal to u2. And likewise, you could have chosen the other way around too. So, so there's a certain symmetry to this picture, and each of these different symmetries give you a different choice of a u. That's the case when eigenspaces are one-dimensional, but for instance, if one of the eigenspaces were two-dimensional, I would have even further symmetries coming from rotations. Because I can take an orthonormal basis for a plane, and I can rotate it. It's still going to be an orthonormal basis. And it's still going to be it's still going to be a basis of eigenvectors. So you see, all this is to say, you go through everything, Gram-Schmidt, all that stuff, but you're always making some choices underneath the hood. Things that you're computing are not unique, okay? Consequently, U is not unique and V is not unique. To obtain the singular value decomposition for A, the original matrix, somehow you need to synchronize the choices you make for this guy and this guy. Okay? What I'm trying to say is this. Say you're trying to compute these so-called singular vectors. You'll be able to compute singular vectors by just looking at this guy, and this is going to give you some kind of a singular vector, and likewise this. But ultimately, what I really want is I want to say A is this guy up to passive transformations. I'll write it like this. Warning. There are many choices for U and V, but to write, which ultimately we're going to do that, to write A equals sigma up to passive transformations, oh, okay, things are good. U sigma V transpose one needs to synchronize the choices for U and V. Okay? So ultimately, this is what we're going to call the singular value decomposition of A. Okay? We're going to need two orthogonal matrices like this that in principle look like they are independent. They are different letters, whatever. But they are, in fact, dependent on each other. Okay? I'm saying this because if you watch Gil Strang's MIT OCW lectures on this stuff, he just computes some stuff and then he doesn't synchronize this and then he's like confused about why it doesn't work. I'm telling you, if Gil Strang is making this mistake, it's an important thing to know. You need to synchronize the choices. There are choices involved. There's symmetries. Okay. Any comments or questions so far? I still haven't told you how to do this stuff, but this is where we're going for now. Well, in order for something like this to happen, for U orthogonal and V orthogonal of the correct dimensions, and while we're at it, let's figure out that the dimensions work the way they should as well. Well, A here is, let's write it. A is 2 by 3. I'll use green. A is given to me as 2 by 3. I told you the matrix capital sigma, okay, that's notation, of singular values of A is always going to be of the same dimension as A. So this, at least for us, is going to be 2 by 3. In order for this matrix product to work, U has to be 2 by 2, V has to be 3 by 3. Otherwise, the dimensionality would not match up. Okay? Make sense? Which, you know, I chose the notation in the appropriate way so that this works too. And again, you don't have to write it this way, but this is very common. This is traditional. So you want to keep the tradition in a sense. So you see this is 2 by 2. V is 3 by 3. Okay. So this we're going to call the singular value decomposition of A, pretty much like the spectral decomposition, something like this, but for an arbitrary matrix. Okay? And then, much like in the case for the spectral theorem, where we had a factorization in terms of matrix products, and then we sort of opened those up to get a linear combination of rank 1 matrices, ultimately we're going to do the same thing in this case, and that's also going to give us another thing that is again called the singular value decomposition. Okay? But first you need to understand how to get to this point. Well, V, okay, V is here. It's orthogonal. Remember what it means for a matrix to be orthogonal. Among many things, it means that its transpose is its inverse. So I can take that V transpose and send it to the other side. I'm starting from the conclusion, so reverse engineering, where we're trying to get to. So this should happen. Okay? This is what I need. Somehow, this sigma matrix 2 is related to the D matrix and E matrix, because if you look at sigma, and if you were to square it, well, what does it mean to square? In this case, take sigma, sigma transpose. Well, if you look at sigma, sigma transpose, you're going to get E. If you look at sigma transpose sigma, you're going to get D. Or maybe it's the other way around, actually, just so that things work. Let's write it. So if I were to take this, this is going to be 2 by 2. It's going to give you D, actually. The diagonal matrix for the first matrix, this part. And if you do it the other way around, you're going to get the other diagonal matrix. Okay. So you see things are getting complicated. We have a bunch of different matrices, but they're supposed to be synchronized to each other. And this is why it's harder to understand what is happening with the singular value decomposition. People use all of these different letters and stuff like that, and then everything sort of determines everything else. Okay. Let's see. What else can I sort of figure out just by basic matrix algebra? Well, another thing you can do is you can just take this equation and plug it into this. That would also give you some stuff, which should give you these. Let's do that as well, just so that you see the sort of connection. So this SVD, if I just plug it into AA transpose or A transpose A, should reduce to these, okay? So this is this times U sigma V transpose transpose. When you're taking the transpose of a product, remember you need to flip the orders. So this is V transpose transpose, which is just V, and then sigma transpose, and then U transpose. V being orthogonal tells you that this is identity, cancels out. Sigma sigma transpose is D, and U, D, U transpose. Okay. All this is to say is that this singular value decomposition of A, when you plug it into this matrix, gives you the spectral decomposition for the matrix. Okay. And likewise, if I were to plug this singular value decomposition into this, it's going to give you this. Let's do that too. Maybe over here. So I want to compute A transpose A. Transpose of this times U sigma V transpose. Again, flip the orders. V sigma transpose U transpose U sigma V transpose. U is orthogonal. This is identity. Cancels out. Sigma transpose sigma is E. So this is nothing but V. E V transpose. So somehow you see again the singular value decomposition, this equation over here, simultaneously includes the spectral theorem or spectral decomposition for AA transpose and A transpose A simultaneously. Okay. Now the final piece of the puzzle is this. How do you even do this synchronization? How do you synchronize a U and a V such that they fit into the singular value equation or SVD equation so that all of these work? And ultimately, in fact, I am here telling you how you're going to figure that out. Okay? So V, you start with some V that fits into this. That is to say, solve for eigenvectors for ATA, orthogonalize, that gives you V. Apply A to it. This equation tells you that the outcome should be constant multiples of columns of U, right? Because sigma, ultimately in this context, is going to correspond to nothing but multiplying or scaling each of the columns. Okay. I don't want to start computing that, but tomorrow that's what we're going to do. Slowly figure out how to do this. V in this case is going to be called right singular values, or rather the columns of V are going to be called the right singular vectors, of A, and columns of U are going to be called the left singular vectors of A. Okay. It's a good time to stop. There's an attendance sheet around. Please make sure to sign it. And then I'll see you tomorrow. All right, let's start. Good morning. We're going to keep working on the singular value stuff. Singular values were pretty much eigenvalues, but for arbitrary matrices. Right? We just like took the matrix and we pushed it into this spectral theorem. And how did we do that? Well, the only hypothesis for the spectral theorem is that the matrix that you're looking into is symmetric. And it just turns out to be the case that if you were to take any matrix and multiply it by its transpose, either from either side, that matrix ends up being symmetric. So you can just plug it into the spectral theorem, and that gives you a bunch of things. Once we sort of basically take all of these different parts coming from the spectral theorem and synchronize them, we obtain the singular value decomposition. Okay, so I want to continue with this example that we have been looking into. I have this A, it's a 2 by 3 given by this, like so, 8, 7, minus 2. Okay, I want to get the singular values first. We had done this, but I'm just going to go ahead and remind you. You can plug this matrix into the spectral theorem in two ways. Either you're going to look at A transpose or A transpose A. Now, in general, these matrices are not going to be the same matrix, but somehow they are very synchronized in terms of the spectral data. In particular, for instance, in this case, A transpose is a 2 by 2. I told you this is always symmetric, and it is always positive semidefinite. Which is just a fancy way of saying that all eigenvalues of this matrix are non-negative real. Okay, positive semidefinite. On the other hand, if you were to look at A transpose A, again by matrix algebra, this is going to be 3 by 3. Again, it's going to be symmetric, and it's going to be positive semidefinite. Okay, I'll remind you here. Positive semidefinite means all eigenvalues are non-negative. Are real and non-negative. There are like other versions of this. Negative semidefinite means all eigenvalues are non-positive. There's also mixed. Then you have some of the eigenvalues positive, some of them negative. Mixed signature is what people would say, is also very important, for instance, in the context of special or general relativity. You look at a matrix like this. This is what is called the Minkowski metric. Specifically, you have these four-dimensional vectors, t representing time. And according to special relativity or general relativity, to dot two space-time vectors like this, instead of using the standard Euclidean inner product, you should be looking at this somehow. This makes things work. So this is like a mixed characteristic or mixed signature, as you see. One eigenvalue is negative, the other three are positive. In our case, things are much nicer. By the way, there's like linear algebra with this as well. But somehow the world sort of turns upside down. Instead of having Cauchy-Schwarz inequality, which, remember, upper bounds the inner product in terms of the norms. If you're using this thing, you have a lower bound That's because instead of using the standard trig function there, cosine, you need to use the cosh, which is the hyperbolic cosine. So everything sort of turns upside down. Pretty fun, but we're not doing any of that. We have this. Well, applying the spectral theorem to this guy and this guy, I have two spectral decompositions, one for this, one for this. Let's write it out. I need to be careful with the notation. Let me think. Yeah, let's start with this, I guess. Applying the spectral theorem to AA transpose gives let me think about the notation. So I need an orthogonal matrix and a diagonal matrix such that AA transpose is orthogonal, diagonal, orthogonal transpose. But I just need to be careful with the notation that I use. Let me see. What do I need? So this is going to be a 2 by 2. So that should be a U. OK. A 2 by 2 orthogonal Q and a 2 by 2 diagonal D such that AA transpose equals U D U transpose. I can write it like this. Yeah, let's leave it like this for now. Okay, this is just a spectral theorem applied to this specific symmetric matrix. And likewise, if I were to apply the spectral theorem to the other way around symmetric matrix, I'm going to get a, oh, this should be U. I'm going to get a 3 by 3 orthogonal, which I'm going to call V, and a 3 by 3 diagonal, which I'm going to call E, such that, again, you have this spectral decomposition. Now, these letters are not super important. It's just that it is common to write the singular value decomposition this way, U sigma V. And so I chose the letters according to that. That's how you see it typically.
Are you going to dock us points if we don't write it like this? Or is this like the standard way?
Say again?
I said, you're going to dock us points if we don't write it like this? Like,
What do you think?
I think so.
No, I mean, no. I never deduct points from not writing the right notation. Yeah. I feel like I'm kind of offended, actually, that you think this way. I would have thought that you would think differently of me. But anyway.
It's not a dig. It's not a dig.
No, I understand. Yeah, you're looking out for yourself. But yeah. Anyway, yes. So you can just use whatever letter you want. But so I'm just trying to sort of present the theory in much sort of compatibility, as much compatibility as possible. It's not that everyone that uses SVD uses this notation, but this is like the most common. Ultimately, my aim throughout this course was so that you guys have, maximized literacy in math. But anyway, so you have this and this. the problem, so ultimately we're going to put these two together to get the SVD. The point was this. You want to synchronize this choice of u and this choice of v, and consequently the choices of d and e as well, but that's a lesser issue, in such a way that we have that. The choices of, let's write it like this, d, u, e, and v. In such a way that no, I'll write it like this. This holds for sigma, the matrix of the same dimension as the original A, with the diagonals singular values. For sigma equals sigma 1, sigma 2, 0, 0, 0, 0. Okay. I'll just remind you what these sigmas were. Sigma 1 and sigma 2 were the singular values. And these are always indexed in a decreasing fashion. Okay, and what were these? How do you compute these things? Well, this is sort of the magic in this business, that even though these two matrices are distinct, somehow, you see I told you here, eigenvalues of both of these are non-negative, and their positive eigenvalues match with the same AM and GM. And sigma 1 and sigma 2 are going to be the square roots of the eigenvalues, positive eigenvalues of either one of these. So have the same positive eigenvalues with the same AM and GM, and these sigma i's are square roots, positive square roots of these eigenvalues of the symmetric matrices. We'll discuss, I think, why this works out this way on Friday. For now, we're just taking it for granted. I'm going to say a couple words later. But this is the issue, okay? This is what we need to do. And insofar as we can achieve this expression, this is called the singular value decomposition of A. Okay, that's the definition. Now, V being orthogonal, I know that V transpose is equal to V inverse, which means that in this expression, in this factorization I want to get, I can send this to the other side and write the same thing as AV equals U sigma. Okay. You can write it like this as well. And because of this, I'm going to call the columns of V ultimately is going to be this passive transformation for this matrix. I'm going to call its columns the right singular vectors of A. And I'm going to call the columns of U the orthogonal transformation for the symmetric matrix obtained the other way around, the left singular vectors. Okay, I'll write it here. So definition of right singular vector. Columns of U are left singular vector. Okay? Right singular, left singular. Now I should ask you, how can I, forget about sort of synchronization, whatever, how can I go ahead and compute these columns? How do I compute singular vectors for A at this stage? Here's a matrix. I'll write down more numerics here as well. We sort of looked into this last time. I just copied it from the textbook. Sigma 1 turned out to be root 360, and sigma 2 turned out to be root 90. So 6 root 10, sigma 2 is 3 root 10. I just computed these. Or at the very least, I told you how to compute. Maybe we should start with that. How do I get these numbers? I'm given this 2 by 3. What is the procedure? What is the algorithm for me to get these numbers?
You just want to basically multiply the matrix by its transpose, and generally you want to find the smaller matrix just because it's going to be easier, and then compute the eigenvalue of that.
Okay. Okay. Okay, so this is very important. Ultimately, you're going to take this A matrix and pretend that these singular values, singular vectors, all of these are eigenvalues, eigenvectors. Say these are eigenstuff. It's just that, you can't just compute the eigenvalues of something like this. But you take this and multiply it like with its transpose, which now gives you a 2 by 2 symmetric. You can go ahead and just run the eigenstuff algorithm. Compute the eigenvalues of this guy. Square roots of those numbers are going to be the singular values of A. And likewise, you can do this as well. You can use this, compute the eigenvalues of this, take the square roots of those, and those are going to give you these numbers again. Okay? So when it comes to computing the singular value, singular vector, SVD, whatever, for whatever matrix, all you need to do is do the same stuff for these matrices. And then take the square roots ultimately. For singular values, singular vectors are exactly eigenvectors for these matrices. And so, does this make sense? And so I keep track of this. Oh, let's also record these as well. Ultimately, the reason why this whole thing is kind of confusing is because there is some rigidity to all of these equations, but also there is some give, right? So you have certain choices. And so you need to synchronize these choices so that things work. Okay? So you need ultimately something like this, U sigma V transpose. Sigma typically is fairly well established. It's pretty much always this, although there are other versions as well. But you want to get this sigma. One matrix, so sigma is fixed. One matrix is this. It's a matrix with the same dimensions as A. And in the diagonal, you put the singular values of A. And then you pad it with a bunch of zeros, depending on the dimension of A. Okay, so the capital sigma matrix is pretty much unique. The issue is, how do you synchronize this and this? And how do you even synchronize D and E? That is to say, ultimately, you want to do all of these calculations in such a way that this equation holds, and simultaneously, this equation holds and this equation holds. I want this, this, and this to hold simultaneously. So it's a system of matrix equations that are nonlinear, actually, because you're multiplying. Okay. Meaning, I want this, and I want this, and I want this. And if you start getting confused about the relationship, you can just plug in A equals this, take this equation, plug it into this, and that should give you some more relations, okay? So for instance, we wrote this last time as well, but I'll do it once more. Assuming that you have a solution, like so. Okay, oh, that's a transpose. This is this times flip V sigma transpose U transpose. V orthogonal means that this is identity, so it cancels out. So you have this. In order for both this and this to hold, then it must be the case that D matrix is this guy. Okay. And in this case, what does it turn into? If I take this and multiply it by its transpose, well, I'm going to get sigma 1 squared, sigma 2 squared, and then padded. Oh, no pads. This is just 2 by 2. Okay? Makes sense? Right, so this is okay because ultimately this D matrix is supposed to be diagonal, and since this is given by the spectral theorem applied to this guy, it should be the diagonal matrix whose diagonal entries are the eigenvalues of this matrix. But since we defined sigma 1, sigma 2 to be the square roots of the eigenvalues, well, the squares of the sigmas should be the eigenvalues of this guy. So it all matches. Okay? And you can do it the other way around too, and that would match with E. I'll do that here too again. I'm just applying matrix algebra. Okay, just look at this again. Flip. That's a transpose. U is orthogonal. U transpose U is identity. It cancels out. So in the middle, I'm going to have sigma transpose sigma. And again, in order for both this and this to hold, well, E has to be sigma transpose sigma. Okay, and what is this in this case? Well, I can just go ahead and multiply this, and you're going to realize this is nothing but sigma 1, sigma 2, and then 0, 0. Okay. So again, these matrices, they're not the same matrix. In general, their dimensions even don't match up, but they're going to have the same positive eigenvalues. Should be squared there. Same positive eigenvalues with the same algebraic and geometric multiplicity. Okay? Ultimately, this block of 0 is padding. What is important is that this matches with this nice block over here. Okay? And really, underneath the hood, which I'm going to say a couple words about this on Friday, I think, this is ultimately nothing but a more fine resolution statement of the fundamental theorem of linear algebra. Okay. And we'll see why later. Okay. Now, I still haven't computed u and v in a synchronized manner. But ultimately, in order for this to happen, this has to happen also. And since I know that v ultimately is going to be attached to this guy, well, I know how to compute this. Right? So the spec of this is square of this, and 0. So this is 360, 90, and 0. And I know at this point in which way I have ordered the diagonal entries of the diagonal matrix associated to A transpose A. And so all I need to do then to figure out capital V is to find one eigenvector for sigma 1 squared, this guy, one eigenvector for this, and one eigenvector for this. Okay? So this V is going to be 3 by 3. Okay? V1 is going to be attached to this, V2 to this, V3 to this. Okay? And ultimately, if you remember the spectral theorem, these are not some random vectors. Indeed, V1, V2, V3 constitutes an orthonormal eigenbasis for R3. Okay? That is to say, they are normalized, their norms are 1, they are perpendicular to each other, and they are all eigenvectors. Right? So V1 is an eigenvector for this guy associated to the eigenvalue 360, and so on. I'll rewrite it here too. For R3, adapted to this matrix. Okay. So how do I compute eigenvectors? Well, I just go ahead and plug this number, say, into the eigenequation and solve. Now I just use the weak one ideas, row reduction, whatever. Okay. Any comments or questions so far? I don't think I'm going to compute these, but I'm going to give you the, the specific vectors that are in the textbook that ends up working. I'm just going to tell you how to compute this because I think at this point we've done plenty of calculations in class. But before I continue, are there any questions about any of this so far? The complication is, as you see, like there are multiple sort of pieces, and we're using everything that we learned in this course. Everything comes together. Yeah.
For sigma, let's assume for a moment that you compute A transpose A and get the extra 0 in your singular value. If you have the extra 0 in your sigma, is that going to be a problem? Or?
So I guess you're saying, say for instance, here it just turns out to be the case that there's only one positive singular value. It can happen. In this case, I would still keep capital sigma to be the same dimension as A. The blocks are like this time, though. But the padding is not only to the side, but to the bottom and to the diagonal also. Yeah.
Thank you.
Yeah. Yeah, I'll give the general format on Friday. I'll say this too, I had mentioned this last time, but due to magical reasons, the rank of A equals the rank of this matrix, which equals the rank of this matrix, which is the same thing, if you think about it, as the sum of the algebraic multiplicities of all positive eigenvalues of this, and likewise this, which means the number of positive singular values here is exactly the rank of A. In this case, the rank of A is 2. If you compute, you can see it. Yeah. Any other comments or questions so far? Yeah, I'll go into the general case later. I just wanted to go through at least one example like this so that you understand. Okay, let's see what else, what I can erase. Okay, I'll write it here. I'll say it like this too. Because of this equation, I typically solve for v first and then synchronize u according to it. But you can do it the other way around too. From this equation, you can send, you take the transpose, so that now you have a u transpose, and then you can send it to the other side, and you can solve for u, which could be simpler because you see u is a smaller matrix. So computing two-dimensional vectors is easier than computing three-dimensional vectors. You can do it either way. I'm just going to go ahead and think about v. To compute vi, capital V, let's say, need, eigenvectors of this. Okay. V1 is going to be an eigenvector associated to the eigenvalue 360. So what do you need to solve? You need to solve this equation. That's what you need to solve. This is the eigenequation for this matrix with eigenvalue 360. So solve. Well, I'll write it like this. Sigma 1 squared V1 sigma 2 squared V2 and then this is going to be 0 because the third eigenvalue is 0. Okay. You need non-zero solutions. For non-zero, V1, V2, V3. Okay. By the spectral theorem again, automatically, once you have one solution for this, non-zero, one non-zero solution for this, and one non-zero solution for this, they're all going to be orthogonal. But they're not going to be automatically normalized. You're going to have to normalize these, okay? So I'll write it here. Don't forget to normalize. Okay. Remember, last week I gave some examples that, even if you do get orthogonal eigenvectors, If you don't normalize, and if you put them in the matrix, the factorization is not going to work. So you have to be careful with that. Okay? And it turns out that in this case, you can just compute them like so. And how do you solve these? Using row reduction, say. I'll write that too. Okay. Sometimes you can sort of eyeball solutions as well, depending on the case. In any event, it turns out in this case, the following solution works. What do I want to erase? I want to keep this. I think I'm going to erase those. One over 3, 2 over 3, 2 over 3. Note that this is normalized, for instance. V2 is minus 2 over 3, minus 1 over 3, 2 over 3. And then V3 is going to be 2 over 3, minus 2 over 3, 1 over 3. Okay. I'm just taking these for granted. It's just that I don't want to waste your time calculating at this stage. So for instance, if I were to say these vectors are exactly vectors as I want, would you agree with me? Right, so I want to say that these are all normalized, and they are pairwise orthogonal. Okay. So let's, for instance, check the norm of V1. I'm just going to dot V1 against itself. So square of this plus the square of this plus the square of this. 1 plus 4 plus 8, 1 plus 4 plus 4 is 9, divided by 9, that gives you 1. So the square root of this, which is the norm of V1, is 1. Okay? That's what it means. That's what I'm saying when I say normalize. You gotta normalize. The vectors, eigenvectors, have to be normal. Their magnitudes have to be normal. They have to be 1. And for instance, if I were to multiply this against this, right, so this times this is minus 2. This times this is minus 2 again. This times this is 4. All divided by 9. That gives you 0. So V1 is perpendicular to V2. Okay. You don't need to check this. This is going to be automatic because you're using the spectral theorem. The matrices you're trying to compute eigenvectors for are symmetric. Spectral theorem guarantees that eigenvectors associated to distinct eigenvalues are going to be automatically perpendicular. Okay? But you're going to have to fix this. Okay? Typically. Okay. And so, once I have this, I have capital V, which is the matrix with columns these. I'm not going to write it explicitly. Okay. Now, again, this is, in a sense, the final part of the magic. It just turns out to be the case that if you were to apply A to any one of these vectors, the resulting vectors 2 are eigenvectors for the other matrix. Okay, I'll write it. So V1, V2, V3 was an orthonormal eigenbasis for R3 adapted to the 3 by 3 matrix. In this case, 3 by 3 is this guy. Again, this is automatic by the singular value decomposition, the theory underneath. Automatically, AV1, AV2, AV3 are going to be either, let me put it this way, either they're going to be 0 or they're going to be eigenvectors. Either are either eigenvectors for the other matrix or zero matrix, zero vector. Okay. And furthermore, the ones that do survive, that is to say, that do end up being non-zero, are going to be eigenvectors associated to the same eigenvalue. Okay, that is to say, you see V1 here, based on our calculations, is an eigenvector that is normal associated to the first eigenvalue, sigma 1 squared, 360. I'm telling you that A times V1 is going to be an eigenvector for this matrix associated to the eigenvalue 360 again. So let's compute AV1 this multiplied by that guy 1 over 3 times 1 to 2. Take the scalar out. The scalar is not going to matter that much. I need to multiply this and that. It's going to give me a 2 by 1. 4 plus 22 plus 22. And then 8 plus 14 minus 4. So this is 44, 48, and then this is 18. I can simplify this a little bit. 16 and 6. Okay. This is going to be automatically an eigenvector for this 2 by 2. Associated to the eigenvalue 360 again. Okay. So eigenvectors with the same eigenvalues, associated to the same eigenvalues. Or 0. Okay. Okay, let's think about this. What I'm telling you here is that A times V1 is going to be an eigenvector associated to sigma 1 squared for this matrix. And A times V2 is going to be an eigenvector associated to sigma 2 squared, again, for this matrix. If I normalize them, well, it's going to turn out that the magnitude of this is exactly sigma 1 squared. And therefore, all I need to do is to factor out the norms, and that's exactly this. Okay. So Oh, this, okay, that's fine. For some reason, there seems to be some scalar issue. Maybe I made an error here, but what I said was correct. Okay. And so ultimately, this is how everything works out. Maybe I should write this explicitly. Take this vector, it's a two-dimensional vector. If I were to put it into the eigenequation for this matrix, I'm telling you this is going to be this. That's what I mean. And likewise, if I were to put 2 here, that would be 2, that would be 2. Now, as it happens to be the case that in this case A is 2 by 3, and I know that the rank of any matrix is the same thing as the rank of its transpose, which means that the rank in this case is at most 2. In this case, it is exactly 2, which means that since I can think of this A as a transformation from 3 dimensions to 2 dimensions, well, some of the things has to die, right? So if I start with a 3-dimensional, with a basis consisting of 3 independent vectors, well, at least one of them has to die if I apply it to it.
I think your mistake was as simple as writing 11, 11 instead of 11, 14 for the matrix A.
Oh, yeah, yeah, thank you. I wrote the wrong matrix here. So if this is 14, that is 28. So I'm adding 6, 54. 54 is 9 times 6 divided by 3. 3 times 6, which is 18. Is this correct? 64. Okay, it seems like it is correct. 18 times 18 is going to give me something whose first digit is 1. First digit is 4. And this is going to give me 36. It seems like if I were to look at the magnitude of this, I'm going to get sigma 1 squared. Or maybe sigma. No, sigma 1. No, sigma. Yeah. Norm squared is going to be sigma 1 squared. Exactly. Okay. Lots of moving parts that sort of depend on each other. What you should keep in mind is, from a practical point of view, you want to apply the spectral theorem to whatever matrix you have. In this case, this. So you look at AA transpose or A transpose A, and you go from there. Okay. We'll talk more about why some of these things work on Friday, but I think it's a good place to stop for today. Thank you. All right, let's start. Good morning. Today we're going to keep working on the singular value decomposition. I really want to transition to sort of like a more abstract understanding, discuss some of the items, why they work the way they do, and so on. So I'm going to give you the more general case with the indices and stuff like that, but we're going to then look into this case as well to see the real complexities of the situation. Yeah, let's start like this. As a summary. So now I want to do the general case a little bit. And maybe I should say, even before I start, is this. A very nice way to think about the singular value decomposition is, well, SVD is spectral theorem plus the fundamental theorem of linear algebra, actually. That's a good way to think about it. So it's everything that we discussed. Spec theorem plus fundamental theorem. Hi.
I cleaned the whiteboard.
Thank you.
You're welcome. Now is Saturday, everybody.
That is true.
Have a good big weekend, everyone.
Thank you. You too. So SVD equals spectral theorem plus fundamental theorem of linear algebra. eigenvalues are pretty much singular values are pretty much eigenvalues. Singular vectors are pretty much eigenvectors. Okay. Singular vector is pretty much eigenvector. Of course, when I say something like this, it comes with some fine print. When I say singular value is an eigenvalue, you start with an A and you need to sort of come up with a different matrix and look at the eigenvalues of that and so on. Okay. So that's sort of the general idea I have in mind. So let's go ahead and try to write things down. I start with an arbitrary n by n. Forget this for a second. Be an arbitrary, maybe I should say general case. SVD. Let A be an arbitrary n by n. Let's write the fundamental theorem of linear algebra and stuff like that too while we're at it. So I can think of A to be a linear transformation from Rn to Rm. Okay, Rn to Rm. What is important in this business is also to think about A transpose. Let's write it out explicitly as well. A transpose is going to be n by m, and it's going to be a transformation from Rm to Rn. Then also, A transpose is n by m, aka A transpose is a transformation from Rm to Rn. Okay. Let's also put R, lowercase r, to be the rank of A. By fundamental theorem of linear algebra, whatever, we know at this stage that the rank of this is the same thing as the rank of this. Okay. By definition, rank of a matrix is the dimension of its column space. If I'm looking at A, for instance, the column space of A is a subspace of Rm, which means that R has to be not greater than M, so it's an upper bound M. And likewise, if I were to do the same thing with A transpose, I would get that N is an upper bound on R. So I have that R is some integer between 0 and the min of M and N. Okay, it could be any one of these, depending on the context. How would you figure out this R? Well, you would need to do some sort of a row reduction, whatever. Maybe in certain situations you can eyeball it, but in general you would need to do some sort of a row reduction. Okay, what else do I want to say? Well, let's record the nullities and so on as well. The nullity of A in this case, right, it's the dimension of the null space. We also know by the fundamental theorem of linear algebra that the null space of A is the same thing as the orthogonal complement of the column space of this. Okay, which means the nullity of A, you can do this in multiple ways, I guess, is n minus r. And the nullity of A transpose is m minus r. So n minus r is the nullity of A, and m minus r is the nullity of A transpose. Okay? This is, if you want, the fundamental theorem of linear algebra version 2. So the ranks of A and A transpose match, okay? But on the other hand, the nullities of A and A transpose in general, I mean, you should not expect them to match. When I say over there, SVD equals spectral theorem plus fundamental theorem of linear algebra, that's what I mean in a sense. Because remember, we're going to look at, for SVD purposes, two matrices associated to this guy. And then for these two matrices, I always told you that positive eigenvalues match, but there could be some zero eigenvalues, and the AMs of those zero eigenvalues are not going to match in general. It's the same thing here. Okay. Okay. Now, perhaps before I go any further, let's record these numbers for this specific matrix. What is R in this case? What is M and N? I need 3 integers.
The rank's going to be 4.
Rank is 4. Do we all agree with this? Okay. Rank is 4. What is M? I need to count the number of columns. 4, 5, 6, 7. N is the number of, number of rows was M. Number of columns is N. 1, 2, 3, 4, 5, 6. So I'm thinking of A to be a transformation from R6 to R7. Okay? So this goes from R to the 6 to R to the 7. Okay. And likewise, A transpose is going to be a transformation, which is a transpose of this. That goes from R7 to R6. And here, as you see, I have a bunch of zeros. You might find it useful to think of this as a block matrix, actually, like so. Okay? And instead of writing 7, 6 here, you could have written 4, 3, 4, 3 here. I'm sort of partitioning the number of rows and the number of columns, 4, 2. So I can write it like this. 4, 3, 4, 2. Okay. So how do we continue with SVD? I want to basically get eigenvalues, right? I need to get eigenvalues somehow. I cannot just look at the determinant of A. In general, it doesn't even make sense because N doesn't need to be the same thing as M. But what I can do is I can look at A transpose A or AA transpose. Now, for sure, these are going to be square matrices. I have this. And this is going to be N by N. It's always going to be symmetric, no matter what A is, okay? It's always going to be symmetric. And all eigenvalues of this is going to be non-negative. In other words, this matrix is always going to be positive semi-definite. Is M by N symmetric and positive semi-definite. Okay, I'm just writing it down for now. If we have time today, we can sort of try to figure this out using just basic algebra, or matrix algebra, let's say. And likewise, if I were to look at AA transpose, now this is going to be, again, a symmetric and positive semi-definite matrix, but its dimensions are going to be M by M. Is M by M symmetric? And positive semi-definite. Okay. again, let's take this for granted for now. How do I want to say this? Well, I can apply the spectral theorem to both this guy and this guy. Okay? So I'll write it like this. Okay. Okay. Applying the spectral theorem to both this and this, I can get a spectral decomposition for A transpose A. Right. So this is going to have an orthogonal, well, I'll write it like this. A transpose A equals V, I think this was the notation that I used last time, VE V transpose, V orthogonal, E diagonal. And likewise, for this, I'm going to get U D U transpose U orthogonal D diagonal. Of course, their dimensions have to match up with whatever dimension I have over there. I'm not writing it again. Okay. Let me just check for a second. Okay, seems correct. The next step is this, okay? So spectral theorem gives you these factorizations, but remember, these matrices are not unique. You have some choices involved. But even if you were to just look at the spectral theorem here, we had a synchronization property. And what was that? Well, in this case, this was this orthogonal diagonalization of this matrix, this product matrix. And in the diagonal matrix E, the diagonal entries were going to be the eigenvalues of this product matrix with multiplicity. And depending on how you decide to order those eigenvalues, well, we talked about how the columns of B should be ordered in a compatible manner. Okay? That is to say, if the top left entry of E is, say, eigenvalue lambda 0, well, the first column of capital V better be an eigenvector associated to that eigenvalue. Okay? You have to synchronize these. But it turns out, again, this is by positive semidefinite property, that all entries of E and D are non-negative. Okay? Many of them are 0, of course. Off diagonals are 0. Some entries in the diagonal could be 0 to begin with, but eventually you have the remainder, and they're going to be positive eigenvalues. And this is sort of the magical thing in this context, that when it comes to positive eigenvalues for this and this, okay, they're going to match. So this has the same positive eigenvalues as this one. And furthermore, the algebraic multiplicities and geometric multiplicities too are going to match. So somehow they're sort of synchronized. So let me write it like this. I'm going to write it like so. Mu I is, say, a positive number, is an eigenvalue of the first matrix if and only if it is an eigenvalue for the second matrix. Okay? Transpose. And in this case, am of mu I is going to be the same no matter according to which matrix you look at. So maybe I can be a little bit more explicit and I can write it like so. Am of mu I according to the first matrix is the same thing as the am of the same eigenvalue according to the second matrix. Okay, I'm not going to write down the GM because as a consequence of the spectral theorem, remember, we know that for symmetric matrices, AM is the same thing as GM. You don't need to write it. Okay? Sigma I is going to be the square root of this number, however many I have. Let me keep writing these as well. Yes. So there's going to be exactly R many with multiplicity eigenvalues that are positive. Okay, R is the rank. I'll write it here. Okay. There are exactly R many positive eigenvalues mu I, but some of them might be repeating, okay, with multiplicity. With multiplicity. The square roots of these eigenvalues are the singular values of A. By definition, is sigma I, which is mu I square root, which is a positive number. Okay? And it is also customary to index these eigenvalues or singular values in such a way that when you increase the index, the number doesn't grow. In general, this is not necessary, but that's sort of traditional. Index so that you have this. Okay? Question? Okay. So this and also squares, if you look at the squares, I have mu1, mu2, and so on. Okay. Any comments or questions so far? Now I'm going to introduce some more terminology or some more notation. I'm going to define capital sigma with a tilde. It's going to be the R by R diagonal matrix with these as the entries. So it's an invertible matrix. Okay. And I'm going to define sigma to be basic to sigma R, sigma tilde, but I'm going to pad it with zeros so that the dimensions match up to the dimensions of A. with zeros to get block diagonal sigma with the same dimensions as A. What does this mean in this context? Means I'm going to start with this, and I'm going to put some zeros like this. These are zero matrices. And so this is going to be r comma m minus r. And then this is going to be r comma n minus r. Okay, that's what I mean. Okay. Now the point here again is that this sigma tilde, you see it's an r by r matrix. Diagonals are positive. It's an invertible matrix. Sigma in general is not invertible. It may not even be square. But at least this sort of core of it, the heart of sigma, consisting of the singular values of A, is invertible. Any comments or questions so far? Okay. Now, I haven't even wrote down the singular value decomposition for A. For that, I need to do some further synchronization. We talked about how in the spectral theorem context, the diagonal matrix is synchronized to V. And in general, even if you were to fix the diagonal matrix, there is not a unique V that fits into the equation. There are still symmetries that you can use, okay? So the choice of E doesn't uniquely define V, and vice versa. I'm saying all this because I remember when I was first learning this stuff, people would talk about the SVD decomposition, whatever, but even though people use the definite article, it's just a SVD. So just letting you know. Then eventually it kind of becomes important to realize that this is not unique actually. But okay, what I do need to do is somehow, first of all, I need to realize that if I need U and V, these two orthogonal matrices, to be synchronized so that I can use them in the SVD for A, then ultimately the choices of E and D are uniquely defined so that this works. Okay. Synchronize the choices of U and V so that A equals U sigma B transpose. Okay. I still haven't told you why you can't even do this synchronization. I'm just telling you, you can. You always can. Okay. We're going to talk about why it is the case that we can. But ultimately, if you require this as well, on top of these two equations, this, well, I should say these orderings together with this, then at the very least, E and D are uniquely defined. I have done this before. all you do is you take this and plug it into this equation, and that gives you E in terms of a capital sigma. Right, so this is supposed to be n by n. To get n by n from this guy, I need to look at this. Okay. This is just going to be, in fact, sigma tilde squared and then with padded zeros. Okay. What does it mean to take the square of sigma tilde? Well, this is r by r. I can just take the square of any matrix like this. Of course, this sigma tilde squared is going to be nothing but the diagonal matrix whose diagonal entries are exactly these. And likewise, D is going to be this guy. And again, it's going to be sigma tilde squared and then padded with zeros so that I have the appropriate diagonal matrix. So you see, even though I'm using these notations, this is not of the same dimension as this. It's just that these zero matrices are, they are of different dimensions. So here, sigma tilde squared is going to be this. And if you want, we can write down the dimensions as well in a nice fashion. So this is going to be like so. Rn minus r, Rn minus r. So that ultimately E is n by n. And this is going to be Rm minus r, Rm minus r. Okay. And how do you synchronize? To synchronize, what does work every single time is this. Let's see. What can I erase? Maybe I don't want to erase. Question? I know this is like rather complicated. So maybe I'll erase this board and then I'll rewrite it again once I'm done with writing everything, so that you have like a complete summary. To synchronize, as mentioned over there, well, you're going to solve either for u or v, okay, such that this works, either one of the equations work, and then you're going to force this other equation, okay. Let me write it like this. Can find, say, an ONEB for Rn, orthonormal eigenbasis of Rn adapted to this matrix. So that our notation works, let's call these vectors v1 to vn. Put them in, even before that, I'll say it like this. It turns out, and in fact, let me write it like so. Okay, I'm writing it like this, but you should note it this way, okay? I fixed the indices of the eigenvalues for this matrix, A transpose A, in such a way that they're in this decreasing order, okay? Because I do that, since I'm trying to get an ONEB that would fit into this, whatever V is, the order of the eigenvectors have to abide by the order of the eigenvalues. That means that in this ONEB, the first R eigenvectors are going to be eigenvectors of this matrix associated to positive eigenvalues, one of these mu i's, and the remainder, this, is going to be eigenvectors associated to the eigenvalue 0. Okay? These are, the first R are eigenvectors associated to positive eigenvalues. And in fact, since I've allowed multiplicities here, I can just say V1 is an eigenvector associated to mu1 and so on. Mu r, and all these are going to be eigenvectors, orthogonal and orthonormal, associated to eigenvalue 0. Okay? Now again, this is the magic. If you take this ONEB, of course you then take them and in this order, put them in a matrix, capital V, and that solves this. What is more magical, or what is further magical, is that if you were to apply A to these vectors, well, it turns out that A kills all of these, okay? Because note, we said that the nullity of A is equal to n minus r. In fact, we can say more. We can say that the null space of A is the same thing as the null space of this matrix. So whatever this kills, A also kills also. A is going to take these to 0, and these are going to survive, okay? And what they're going to turn into are going to be eigenvectors for the other matrix associated to the same eigenvalues. Okay. AV2 AVR, and then all zeros. These are going to turn to 0 under A. Okay? So I cannot just say AVN is going to be an eigenvector, because I'm telling you that's going to turn to 0. And we talked about how 0 cannot be an eigenvector by definition. It doesn't say anything. So you see, these positive eigenvalues, initially I wrote for this guy, but what I'm telling you is, if I look at eigenvectors associated to positive eigenvalues for this, and if I push them from Rn to Rm using A, the output vectors are going to be eigenvectors for the other matrix associated to the associated to exactly the same eigenvalues. Okay. Then what you can do is, well, first of all, again, it's going to be automatic. The norm of each of these vectors that end up surviving are going to have magnitude exactly sigma I. So magnitude of the first output is going to be sigma 1. Magnitude of the second output is going to be sigma 2, and so on. It's going to be automatic. And sigma r. The remainder, of course, have magnitude 0, but they died already, so I'm not really worried about that. Okay? Consequently, if I were to look at AV1 and divide it by sigma 1, which I know is a positive number, Okay, it's a positive number. I can divide it. Well, I'm going to get a normalized vector. Those vectors that I end up getting are I'm going to call u1 to ur, and I'm going to use I'm going to find some of the normalized vectors for the 0 eigenvalue. So u1 is going to be av1 divided by sigma 1. u2 is going to be av2 divided by sigma 2. And then ur is going to be avr divided by sigma r. So the first r columns of u here is going to be, again, defined this way. That's synchronization. For the rest, you can just do, again, some sort of a Gram-Schmidt whatever. So you just add a couple more vectors on top of this. um. Okay. And like I said here, the first r vectors in this v basis, let's say, are going to be eigenvectors associated to positive eigenvalues. I push each of these vectors to the output space using A. The end results are going to be eigenvectors for the other matrix associated to the same eigenvalues insofar as I'm looking at eigenvectors associated to positive eigenvalues. Some of these are going to die because they're vectors associated to 0. And so for the basis of Rm, I'm going to have the first R vectors given to me by this procedure. Then I'm going to have to do some more stuff to get the remainder. OK. And ultimately, that's it. And just like we did with the spectral theorem, you can basically open up this expression as a finite linear combination. And let me see. Once you do that, you realize you can write it like this as well. Sigma I, ui, vi transpose. OK. Pretty complicated. Any comments or questions about this more general case? I mean, if you have a question, you should ask now, because next week or the week after, you're going to be responsible for this stuff. OK. Yeah, so there's a bunch of like moving parts, and you need to synchronize them ultimately. Now, the way I think about it, of course, is that this should be, again, this equation should be much like the spectral theorem, telling you that A is pretty much sigma. So OK, so you have this m by n, but ultimately, up to passive transformations, you turn this A matrix into this matrix. You see? So this is what is called a sparse matrix. It's a matrix, most of whose entries are 0. You want to get matrices that are sparse. Another word for this is the L0 metric. So you want to minimize the L0 metric. But anyway, there's a couple more things that I could say here. But I think at this stage, you get the main idea. I want to go ahead and look at this numerical example.
Quick.
Yeah.
Just a question about synchronization. So obviously one of these, so between like the two like U and B,
Yeah.
one of them is obviously going to be larger, and the larger one is going to be padded with zeros. Correct?
Yes.
So generally, is it going to be better to like compute the the work left?
It doesn't matter. It doesn't matter.
Ending up like about the same work?
Yeah.
Either way?
I mean,
Because like my intuition is if you compute the larger one first, right, and then you send the matrices. So like obviously the padded one for the zero eigenvector
yes.
isn't gonna have any like weight in the smaller of the matrices because it's associated to like zero as an eigenvector. Like
Well, I mean, that's not going to matter that much. What it is, I guess what I'm trying to say is this, okay? So if you start with this guy, from a sort of practical point of view, standard operating procedure. So this is going from Rn to Rm. Ultimately, you want to get A equals U sigma V transpose. Presumably, the first thing you want to compute is the sigma. And how are you going to compute it? Well, you're going to look at A transpose or A transpose A. Like you said, so in this case, for instance, this is going to be M by M. This is going to be N by N. Now, either this A is tall and thin, or it's short and wide. And in applications, that's what you see all the time. These have sort of like certain interpretations depending on the field, but let's try to draw. So either like this, or it's the other way around. Okay? In this case, I'm telling you that there are more columns. So this is a fat matrix, like so. That's your A. In this case, this is like a tall matrix, like this. Okay? If this is the case, presumably, in this case, you want to look at this guy, because A transpose is going to be like this, and A transpose A is going to be like this. Okay? And in this case, it's going to be the other way around. A transpose is going to be the big square matrix. A transpose A is going to be the small square matrix. Now, for singular values, depending on your relationship with N and M, so depending on the shape of your matrix, you want to go for this or this to get the singular values. Because singular values are going to be square roots of eigenvalues of these guys, the positive ones. Okay? So choose, depending on your A, either choose this and this, solve for a characteristic polynomial, all that stuff, get sigma, tilde, and sigma. Okay. Yeah, so the next step is, your colleague was asking about this synchronization part. So once you have sigma, you have sigma this way. Now you need to get U and V. The point is which one you're going to get first. Because A equals U sigma V transpose, okay, I like sending this to the other side and write it like this. No matter the dimension of A, because ultimately I'm used to this order of U sigma V, I like this, and I will draw the first compute eigenvectors for V, even if it were larger. Okay? Why? Because I can just go ahead, compute eigenvectors for V, okay? Do an O and EB, whatever, Gram-Schmidt, push these vectors to the other space. I know that the outputs are going to be orthogonal with magnitudes coming from the sigma. That helps this way. What I'm trying to say, let me just finish this. If it just so happens that instead of V, U is small, what you can do is instead of computing this, you can apply transpose to it. V transpose. And go for this. So either this matrix is small, in which case you can solve for this, or if this is the large one, then take the transpose and look at the SVD of the transpose, in which case you can just solve for this and again push.
I was going to say, I guess kind of the heart of my question, even though it's not necessarily relevant for calculations, is if, like, let's assume V, it's going to have dimensions of n, right?
Yeah.
So V has dimensions n. Let's say n is larger than m. So V is the larger matrix.
Okay.
So if you were to compute this ONEV, and you just put these positive eigenvectors associated with positive eigenvalues through A, would you have to do any extra calculations to get, like, besides normalizing the vectors, or like, is there any other?
No. This part is going to be automatic. This part is going to be automatic. This part is going to be automatic. You don't need to calculate the magnitudes as well. Magnitudes of the pushes of positive eigenvectors are going to be exactly singular values. Okay, yeah. For the padded parts, you're going to have to do some more work. In principle, you don't have to, because that's why you see this is a little bit more frugal. Here I'm saying use orthogonal, I need n vectors, whatever. But when you think about it, because the sigma matrix has this 0 here, when you do this multiplication, in fact, the eigenvectors of u associated to the eigenvalue 0 are going to 0 out anyway, actually. So this, in the sum, I'm adding all the way up to r. Yeah. Any other comments? Okay, I don't want to start the new problem. So this example that I wanted to discuss, we're going to do that on Monday, but that's going to be it for this week. Thank you.